Okay, so let's look at this very important proof, the Heine-Borel theorem. And this important theorem, Heine-Borel. And Heine-Borel is important because it characterizes compact sets in Euclidean space Rk. Um, so the definition of compactness, which we went over here, this definition here, which involves uh, finite subcovers of open covers, right, is involved, very involved in using it and applying it. So it's helpful to have a characterization that is in terms of closed and bounded sets, right? So here's the statement. The statement is that a subset of Rk is compact if and only if it is closed and bounded. Okay, so let's go ahead and get started with our proof. So our proof here is for, so our hypothesis is going to be that E is a subset of Rk. And first, I'm going to show that if E is compact, then E is closed and bounded. So I'll say that I'm assuming that E is compact. That's our hypothesis. The claim is going to be E is bounded and E is closed. Okay, and now let's go for the proof. So we know that E is compact. First, I'm going to show E has to be bounded. Now, since E is compact, every open cover reduces to a finite subcover. So I'm going to start off by saying let's consider the following open cover. Okay, so since E is compact, every open cover of E reduces to a finite subcover of E. Consider the following open cover of E. So I'm going to say script U is going to be the set of U sub M, M and N. And now, what is my definition of U sub M? U sub M I want to be defined as the set of X and R, okay, such that the max, doesn't even have to be the max actually, could just be the set in R such that the distance between X and 0 is less than M. So this each U sub M is an open set. It's an open ball that's centered at the origin, and it has a radius of M. You get that picture here? So if K is equal to 2, then like here's U1, U2, U3, U4, right? And so now if we look at script U, which is a collection of all of these U sub M's, since the union of U sub M, M equals 1 to infinity, is equal to Rk, it must be that E is contained in the union, right? Does that make sense? Let me add a page below. Okay, so script U is an open cover of E. Since E is compact, there exists a finite subcover. So you say M1, M2, all the way up to MK in N, such that E is contained in the union of these M sub J. J starts at 1 and stops at K. Right, so there exists a K in N, and there exists these indices, right, such that E is contained in here. So in other words, so this set of U, M, J is in between 1 and K, is a finite subcover of E. Okay. Let M be the max of the set of MJ, J in between 1 and K. Right? Now notice that our sets here are nested. So our sets are nested. U sub M is a subset of U sub M plus 1, and this is true for all M. Right? So then E has to be really in U sub M. Okay? And now since U sub M is bounded, this is a bounded set. So E is also bounded. Okay. Okay, so we've shown that E is bounded. Now we need to show that E is closed. Okay. Now we've got several different characterizations of a set being closed. The complement is open. The set contains all its limit points. The set is equal to its closure. The one we're going to go with in this case is we're going to show that the complement of E is open. So let's put here next. We will show that E complement is open. Remember, a set is open if it's equal to its complement. So all we have to do is say, suppose you have a point that's not an E, we'll show that there exists an R greater than 0, such that the points that are within R units of our point that's not an E, all those points are also not an E. So let X naught belong to RK, but not E. We want to show that X naught belongs to the interior of E complement, i.e., there exists an R greater than 0 such that this set here, which is going to be the set of X in RK, such that the distance between X and X naught is less than R. We want this to actually be a subset of E complement. Okay, so here's how we're going to do it. Again, we're going to use the fact that E is compact, so any open cover reduces to a finite subcover. Okay, so define for each M and M, define V sub M to be the set of X in RK, such that the distance between X and X naught is bigger than 1 over M. So now what does this look like? So here's our picture. Suppose this side is E, right? So suppose here's E, and then on this side has to be E complement, right? And let's say this is our X naught. Okay, so V sub M is going to be the set of points whose distance from X naught is more than 1 over M. So V1 means, okay, if this is 1, I want all the points whose distance from X naught is more than 1. So I'm looking at everybody out here. So all of that is V1. Does that make sense? That's V1. Now what about V2? for V sub 2 is all the points in R, K, whose distance is bigger than 1/2. Okay, so now I've got to come in, and here's 1/2, and I want all of the points whose distance is bigger than 1/2. So that's V sub 2. And then I'll have V sub 3. V sub 3. Now I'm getting in even closer, so now I want all the points that are within 1/3, right? So something to notice, note that V sub n, or V sub m, is a subset of V sub m plus 1, okay? And this is true for all m. Note that the union of V sub m is RK, not X naught, right? Since X naught is not an E, E is a subset of the union of V sub m. So that means that
it's 11:15.
Thank you. Script V, which is a set of these V sub m, is an open cover of E. But now wait a minute. You should be saying, Kalila, wait a minute. How do we know it's an open cover? Well, it's an open cover because each of these sets is open. So each V sub m is open in RK. How do we know that? The complement is closed. So remember, that's what we had. We had our example. What is the complement? The complement is going to be the set of points whose distance is less than or equal to 1 over m, right? So that is a closed ball centered at x naught with a radius of 1 over m. Okay, so since those are closed, which you proved that as part of your exercises, that means that the complement is open. So our cover consists of open sets. Now remember, E is compact. So we'll say, okay, so back to our proof, because that's just kind of to explain what's happening here. Okay, so for each M, we define these open sets. Then script V, which is a set of V sub M, is an open cover of E, or for E. Since E is compact, script V reduces to a finite subcover. In other words, there are finitely many, right? In other words, there exists finitely many V sub m which cover E. So since there are finitely many, that means we can take, right, because remember they're nested, right? So they're nested like this. So if we have finitely many, that means that there exists some m naught such that E is contained in V m naught. Because these V sub m's are nested. Remember, that's the set of X in RK such that the distance between X and X naught is bigger than 1 over M naught. Okay. So if E is contained in one of those, right, that means the complement, or almost the complement, so the set of x and rk, such that the distance between x and x naught is less than 1 over m naught, this has to be a subset of E complement. So every point in here can't be in E because E is, let me show you. So every point in this set can't be in E, right? I.e., every point in here belongs to the complement of E, because if you had a point in here, then that point can't be in E because every point in E has a distance from x naught that's larger than 1 over m naught. But now this use r equal to 1 over m naught. This is an r ball centered at x naught that is contained in EC, the complement of E. So x naught belongs to the interior of E complement. Okay. So we've shown that if a set is compact, then it is closed and bounded in RK. And the second part of this proof, because this is an if and only if statement, will be to show that if you have a set that is closed and bounded, then it is compact. So the proof, the other direction of the proof, I will leave to you. It requires proposition 13.13 in the textbook. And so go ahead, read that, and then you'll be able to understand the second implication in this proof.